Hello everyone, welcome back to Spectrum Classes. This is our part 2 video on the topic origin of shielding in NMR. In the previous video, we have discussed that the shielding constant is the sum of sigma local, sigma neighboring and sigma solvent. So here sigma local is the sum of again sigma d local plus sigma p local, where d stands for diamagnetic and p stands for paramagnetic. About these terms and sigma local we have discussed in detail in my previous video. So if you really want to understand these terms, please go and check that video. And here in this video, we are going to discuss about the sigma neighboring. Sigma neighboring can be understood in terms of sigma isotropic, sigma anisotropic, or sigma ring current. Here, these terms isotropic and isotropic may be new for you. Let us first discuss about this term isotropic and anisotropic. So, if you are having three dimensions x, y, and z, and you are going to study any of the effect, and if that effect is same from all three directions x, y, and z, then that is called isotropic. If the effect which you are going to study is different from different directions, then that is termed as anisotropic. And ring current is applied for aromatic rings. So we are going to discuss this later. Third part is sigma solvent. This we have already discussed in our previous video. And now we are going to discuss about the sigma neighboring, why it is important to study and what does it mean. So here I have collected few examples. So this is the CH3, which is sp3 hybridized. Here it is C double bond CH, which is sp2 hybridized. Here it is C triple bond C, which is sp hybridized. And this is the aromatic ring, which is again sp2 hybridized. So here I have given the contribution of s orbital. So we are having 4 orbitals, 3 plus 1, 4 orbitals. So contribution of s out of these 4 is 25%. Here we are having 3 orbitals and contribution of s out of these 3 orbitals is 33%. If we are having sp orbital, then both orbitals have contribution 50-50%. Again 33% here. If in the absence of any electron withdrawing group, what you see, the chemical shift value for the CH3 is 0.9, whereas for C double bond C, it is within the range of 4 to 8. And for C triple bond C, it is within the range of 1.5 to 3.5. And for aromatic ring, it is 6 to 9 ppm. These are the chemical shift values. So no electron withdrawing group is present, say here, then we can explain this in terms of contribution of s orbital. So more is the s character, more is the acidic nature. Acidic nature means electron withdrawing effect will be more. So it is fine. We are having 0.9 to increased value of chemical shift value, but it is high increase more than we expect. And if it is so, we can explain this in terms of s character, then it should be higher than this. But no, we are having lesser chemical shift value for C triple bond C group, right? So how we are going to explain this? So something is there on which basis we can explain. Here we are again having different chemical shift value range. It cannot explain on the basis of the S character only or electron withdrawing effect. Something is there which needs to be understood. So that is why we are going to here discuss this neighboring group effect. Here in this video, I am going to discuss the neighboring group effect with respect to this C triple bond CH. Here H is the proton on which we are going to see the effect of HC triple bond C. So let's start with the explanation. So that is why sigma neighboring is important. So neighboring group contribution arises from the current induced by B node. You may find this statement difficult to understand here only, but please keep watching this video to understand this statement as well as the sigma neighboring effect. So current induced by B node in nearby group of atoms. This can be explained by taking the example. Here we are having HY molecule. So as I said earlier, Y is our C triple bond CH, right? And here is the H. So we are going to study the effect of Y, or we can say C triple bond CH group on this proton. When we place this HY molecule in the applied external magnetic field, it generates a current in the electron distribution about this Y. So C in C triple bond C, the applied external magnetic field generates electric current in the electron distribution of the Y. That I will explain in a pictorial manner too in the next slide. Okay? And give rise to a induced magnetic moment. So this applied external magnetic field generates electric current about the electron distribution of Y, which induces magnetic moment or magnetic dipole moment, which is proportional to B naught. Here this mu induced, or you can say mu induced magnetic dipole moment of Y is proportional to B naught, and if we remove the proportionality constant, then we are having this proportionality constant. And this proportionality constant chi Y is a tensor describing the magnetic susceptibility of Y. It's a tensor quantity. This in the next slide I am going to discuss this. And here chi Y describes the magnetic susceptibility of Y. In layman language, if you really want to understand this magnetic susceptibility, is the ease with which this Y part of the molecule can be magnetized when placed in the applied external magnetic field. So what inference we have made out of these statements? So simply you just remember this point that when a molecule is placed in the applied external magnetic field, that applied external magnetic field induces magnetic moment which give rise to a magnetic field which is experienced by the neighboring nuclei. So neighboring nuclei will experience the magnetic field which is induced in the Y part of the molecule. Okay. So if you still find it difficult, then in the next slide I am going to discuss. Here we are going to discuss that what is called tensor quantity. Anisotropic electron distribution means electron distribution is different in different direction. The shielding is described by a tensor. A tensor is a concise mathematical expression of the anisotropic property of physical system in three-dimensional space and has the following form. So it is a mathematical expression for a tensor. It describes the chemical shielding if the magnetic field were along x-axis, y or g-axis under conditions of rapid tumbling. Because of that rapid tumbling, which is generally the case of solution, and when we are having our sample in the solution, then under the conditions of rapid tumbling, it can be averaged out and it can be represented as sigma is equals to 1 upon the sigma xx plus sigma yy plus sigma gg. So this is what we are going to discuss here. So suppose we are having a molecule, as I told you earlier, that this H C triple bond C is the Y part of the molecule. If we place this HY molecule along this B naught applied external magnetic field, which is arbitrarily chosen that it is along G axis. Conditions of rapid tumbling, so we can have three different ways to arrange this HY molecule in this applied external magnetic field. One is in the parallel direction to this B naught. The second is in the x direction, and the third one is in the y direction. Okay, so these two are x direction and y direction, both are perpendicular to this B naught, and this is the in the g direction it is parallel to this B naught. So when it is parallel, it is represented by chi parallel, chi perpendicular. Suppose this is the x direction, and chi prime perpendicular if it is y direction. These are arbitrarily chosen relative to the B node. So here this delta B nucleus can be represented as 2 times psi parallel B naught upon R3. What is R? R is the distance between this HY bond. So R is the distance. So the shielding constant inversely proportional to the cube of the distance of the nuclei of interest from the induced magnetic moment. Here we are having this chi perpendicular B naught upon R cube and again minus chi prime perpendicular B naught R cube. So these three orientations this molecule can have when it is placed in a B naught field. Since this is in solution, then on averaging over all orientations of the molecule, the contribution to the shielding constant of the nucleus at a distance r has the following form. So here is the shielding constant. Okay, so which is equal to minus 1 upon 3 r cube 2 chi parallel minus chi perpendicular minus chi prime perpendicular. So I hope you understand these three terms. This is the magnetic susceptibility. Okay, fine. Since this molecule is of axial symmetry, then H is present on the axis of the symmetric axis. If this is not the case, if it is not having the axial symmetry, then this H may arrange at certain angle to this principal axis of the molecule. Then the direction of H can be read from B naught to the angle which this proton makes from this B naught field. In that case, if the molecule is not having axial symmetry, this formula can be converted into this form. Here theta is the angle which is this H makes from this B naught if the molecule is not axially symmetric. Here what you understand, if the magnetic susceptibility, that is chi, is independent of the orientations, whether it is parallel or perpendicular, it is independent of that, the molecule is said to be isotropic and the local field on the neighboring effect is average to the zero. If it is varies with the orientation of the molecule, as I told you earlier, if you are studying any effect from different directions, if it is different in different directions or it varies with the orientation of the molecule with respect to the magnetic field, then that is called anisotropic. The local field may average to non-zero value. So here your neighboring group effect is important. It play important role. So what inference we have made out of this neighboring anisotropic effect arises from anisotropy in the magnetic susceptibility of nearby atoms or positions of the molecule. So this is the theoretical interpretation of this magnetic anisotropy. Now I explain this with example of acetylene molecule.